It's because of the promise and the fear of missing out, mainly, right? If you are not in early, then you may not be a leader even later. What you do with quantum bits is actually you set, let's say, the probability of every possible combination of light bulbs instead of individual light bulbs.
Should all the software engineers be jumping onto quantum computing now?
If you are interested to know and follow, you should do it because it's easier than you think as a developer.
Constantin, Charlee, how are you doing today?
Pretty good. Thank you. You?
Yeah, myself pretty good. Very excited to talk about this. A lot of hype, and hopefully we can unveil some of that. So my first question to you is, how did you end up in the quantum space? How did you end up working on quantum computing?
I ended up in the quantum computing space in probably a less traditional route. I came to Wells Fargo as an intern while I was working on my master's in data science, and I ended up on Constantine's team, and he was beginning to build the quantum computing efforts at Wells Fargo, and I was invited to take a shot at helping. And so everything I've learned on the job over the past couple years, it's been an interesting path, a very different approach to the discipline than I've had in the past in academic settings. Much less structure, much more complexity.
So I started at a different financial institution. Maybe a bigger question is, why are banks even looking at quantum computing at this stage? And the answer is, if you look at what happened with classical computing at the end of 1940s, let's say, you'd only see toy problems being tackled. But banks didn't initially look at them. But then 20 years later, every bank had a mainframe. So now it's better to be there early and be quantum ready when the hardware will become available for large-scale production.
So is this just a technology bet at this stage, or are there any particular applications that are particularly pertinent for a bank?
We do work on real computers because we partner with IBM and others, right? So we do have access to the best quantum computers, but we cannot use them in production yet. In production right now is random number generation, entropy kind of devices. Some companies sell those, so you can use them to get truly random numbers. Applications in networking, encryption, quantum sensing. But in order to solve problems that currently we solve with classical computers, we are a few years away from that.
I guess the first question I should really be asking you is, within all this hype that surrounds this mist of mystery that surrounds quantum computing, and for a lot of people, they've heard of a Schrodinger's cat, and they know there's some kind of paradox involved, but they might not have a good idea. Why is quantum computing a big deal? Why should we care?
It's because of the promise and the fear of missing out, mainly. Right? If you are not in early, then you may not be a leader even later, right? So that's the main reason. We expect that something will come out of quantum computing. We don't know exactly when, and we don't even know exactly what problems will benefit from a quantum approach. If you look at what happened in artificial intelligence, there was a winter, right, when nothing happened outside some small circles. And then once the hardware caught up, improvements like optimizers or starting with the random weights that people cannot explain why they work, but they just work, right? So if you have the hardware, you test some methods and they work, right? You don't need a theoretical explanation. Now, quantum computing is in the stage where we have to deal with theoretical complexity. So we expect something will come out of quantum computing, and that's why we are in it.
Which begs the question, what do we expect quantum computers to be able to do that classical computers can never achieve? What's the holy grail?
What is easy and works right now is random numbers, truly random numbers. So you can sample from probability distributions that are intractable classically, So we know that will work because we use at a small scale, quantum networking. But in terms of solving difficult problems like optimization, the key is the quantum parallelism. The word parallelism is used here in the computing sense, not parallel universes. So you can change the whole state of a quantum system with one single gate. If you have 42, you have over 1 trillion numbers, probabilities that you change with one instruction. Right? So that is the quantum parallelism. And the measurement in itself, if you look at algorithms like Grover, the key there is the measurement. So you increase some numbers, which are probabilities, and because of that, you get an outcome with higher probability. We could increase those numbers classically in a database, but nothing happens, right? You can just say, hey, database, give me the entry with the highest value in this column, because that's a hard problem, right, in itself. Measurement and quantum parallelism are what we see as the key features.
Where are we with this today? Can I go to a shop and buy a quantum computer?
You can buy a quantum computer from any of the manufacturers that make them, or most. Cleveland Clinic, I know, has purchased one. And I believe there is at least one academic institution in the US that has one on their campus. Most institutions most likely will not buy quantum computers in the near future. We need the hardware to get quite a bit better, but before it has meaningful use. But you can buy one if you would like to.
Not as a replacement of your laptop, though, right? Because quantum computing is very specialized computing. I think there is a company in Australia that sells some small photon-based computers that work at room temperature as well. But they are more like toys. Even the big ones are more like toys right now.
Expensive toys too, I assume, right?
Yeah. Yeah.
Very expensive choice, yes.
So from the point of view of researching the quantum computing, do you do most of your work on these toy computers? Do you use simulators? How do you expecting the hardware to catch up? And during that time where you have to wait it out, what do you do? And how does it help or not help your research?
We use simulators. We have our own simulator written in Rust. We call it Spinoza. We also have a Python simulator, although the Spinoza is our high-performance simulator. We utilize simulators for understanding the expected results. And then, of course, we experiment on the real computers as well. What we expect to see, IBM has their roadmap for their expected advancements over the next couple years, and other manufacturers as well have their anticipated dates of having more qubits, allowing more circuit depth. But we are working with the tools we have now and trying to get a good estimate of when we'll have other tools.
Yeah, and the key is we solve problems at a small scale, let's say optimization problem. In the book, we use the knapsack problem. The developers are familiar with it, or at least they studied it in computer science programs with just a few items. On the knapsack problem, you have a limited weight of that the knapsack supports, and you put, let's say, stolen items in it, and you have to decide which ones do you pick in order to optimize the value. So we have the weight and the value.
Right.
So we use in the book initially just 3 items so people can understand, right? And we run the example completely. But again, if you use this for portfolio optimization with 42 stocks or instruments, then you have 1 trillion options of choosing or not choosing something, right? So we know that if it works at a small scale with 5 qubits, 10 qubits, then it will work with the million qubits if we have them.
First of all, thank you for using number 42 in your examples. Very much appreciated the reference.
So it's the first one that takes over 1 trillion. And also it's in the famous book, right?
Yeah, the Hitchhiker's Guide to the Galaxy. One of the all-time favorites. So how many qubits can you actually go and buy today? If I go to Walmart, how many qubits am I going to be able to get?
127, I believe. I may be wrong about that. Yes, IBM has 127. Am I missing anybody that has more?
There are a lot of claims. And what's worrying for me when I see these claims, someone says they have more qubits or more logical qubits. The other competitors criticize that announcement. That doesn't give me confidence, right? I would like to see consensus on what we have. But this is normal in a business environment. There is competition. Our largest computer is 128 or 27, right?
And just very curious, like I've heard all these things about how it needs certain temperatures and how it's brittle and how you need to do all kinds of crazy maintenance with that. Is it at a stage when you just buy it now and you can use it and you can run things on it? Or is it still like an experimental thing that takes a big room and requires weird chemicals?
What we use is that the computers are at IBM's facilities. We use them remotely, right? And at least the superconducting qubits, they require the freezer, low temperatures. Now, the photonic version uses photons at room temperature, but the measurement, I think, still needs lower temperatures. As far as we are concerned, these are implementation details. We care about how do we use any kind of qubit to solve business problems.
Speaking of which, you're trying to solve a certain business problem by writing a book. Who's the book for?
First and foremost, for people like myself. So developers with a programming background who are trying to learn how to write software for quantum computers. But we tried to make the book approachable to anyone with a high school, freshman, year of college, maybe backgrounds. A little bit of math, but nothing advanced, and a little bit of programming experience. Throughout the book, we use Python. As I mentioned, we have also a simulator in Rust. We tried to make as broad of an audience as possible. So it's intended for people with that sort of backgrounds.
I would add that typically in the team, we have researchers and developers. Researchers have PhDs. They understand advanced math, Hilbert spaces, and so on. Developers know how to write code, but as a quantum developer, you need to understand what's behind it. And a lot of books and a lot of developers, I think they expect just to learn the syntax in Qiskit, and they may think they are ready to go, but it's not the case, right? Because if a researcher creates an algorithm and you need to implement it, you need to understand that algorithm, right? As a developer, you may not be able to create it, but you need to understand it and implement it. We have very good success stories. Charlie is one of them. Previously, in my old job, someone else who came out of college also did what Charlie is doing now. We actually have an algorithm called the Grover Optimizer with Stefan Werner from IBM, which is in one of the 5 optimizers in Qiskit, right? But he was out of school. I tested on my kids when they were in high school. So I asked my daughter to write a Julia version. I gave her the Python simulator, which was like 200 lines of code. And she did it. It's on GitHub. She's in a neuroscience lab at University of Pennsylvania now. My son did that in Google Sheets, and he's doing philosophy and history. He's not pursuing any technical career. And I just posted today on LinkedIn. We have a high school graduate, Naren Satish Kumar, who implemented an interactive app to play with multi-qubit circuits, frequency encoding, and function encoding, which is coming in chapter 10. He's going to UCLA, so he's a smart high school student. But it's possible, right? First year, let's say motivated students, they can use our book.
So you start with foundations, right? What are the foundational things that everybody needs to know to basically make the best use out of the rest of the book?
You have two ways, and I'll let Charlee chime in again. She has a very good perspective as a recent graduate who learned this from scratch. So I always value that. So if you look at advanced books, they start with the four postulates of quantum theory. And it took a lot of time, trial and error, 100 years ago to get to those. They're very simple, right? But you put quantum state at the center. There is no qubit in quantum mechanics, right? Now, you start with qubits or you start with quantum state. And our approach was to do both in the end. So the foundations are understand quantum state, understand how the quantum state changes, which is the second postulate. How do you put two systems together, which is how do you add another qubit, that's the composition. And the last one is measurement. So these four postulates are also the foundation. We may not say that in the book explicitly, so we don't scare people when they hear words like postulate, but we follow those ideas. And after that, we build a circuit, and also from a programming point of view, we have strong opinions. The state is as simple as a list of complex numbers. Any developer understands that, an array or list, right? In Python, you can use a list. And then you just explain how you change that list, how you expand the list with another qubit, instead of going straight into circuits. So this is a functional approach. So we use functions. And then we wrap this into an object-oriented implementation for a circuit, and we follow Qiskit's interface, but with a very simple and very efficient implementation. The simulator will be much faster than Qiskit, but it's because Qiskit does a lot of other stuff, like transpilation, optimization, right? So developers can understand how it's implemented. They learn the Qiskit interface that we follow closely, but also how it's implemented. And this approach, if you look at deep learning, for example, with Andrew Ng, if you take that class on Coursera, first you implement a neural network from scratch, then you start using Torch, right? So that's our approach too, right? And Charlee, you can give your perspective on what's foundational based on your experience.
We have what Manning, who is our publisher, calls a mental model, which is just a diagram of sort of the concepts that we are trying to capture. And so in the first third of the book, you learn each piece of that mental model. So that's, as Constantine already mentioned, changing the state and measurement. So you learn them, we talk about them, each of those concepts, and then we implement them, how to simulate them in Python. So we show how we represent the state in our simulator, how we simulate measurement, how we simulate changing the state. And so that's the foundational concepts in the book in the first roughly third that we want the readers to grasp.
We also explain every gate. I think 8 gates are the most important. And we explain them in words when we can. And at least 5 of them you can easily explain in words. And we found out a lot of people, when they just start with the interface in Qiskit, they don't know what the gates do. They just know, oh, I apply RY, the Y rotation, but they don't know what that does. We go with a visual approach, we go after the intuition.
A lot of people who listen to this podcast are going to be coming from software engineering background, and they probably have heard many of the words you just used, like qubit. But other than some kind of intuition from other sources about what it is, it's probably not super clear what it actually means. What's this magical qubit? Can you give us a little bit of intro to that?
So if people have knowledge of binary strings, the outcome of a computation on a real quantum computer is a binary string. Each qubit will be 0 or 1. So you have outcomes and you have qubits. Outcomes are made out of 0 and 1s coming from the qubit. So a qubit, from a computer science point of view, is a digit in that outcome. You can say that for people who understand that. Now, physicists will look at it as a particle or spin up, spin down. When we try to explain this to people without a computer science background, we use light bulbs. So we can think of, let's say, a row of light bulbs. And these are the qubits. Each qubit is a light bulb. So classically, it's similar to the bits where you use a switch and you turn each of them on or off. And let's say then you power this row of light bulbs. Then you know exactly what you get. Whatever you turned on will be on. Whatever you turned off will be off. And it's not an analogy because you can write code for this and it will work. It's a model. It's not an analogy. What you do with quantum bits is actually you program them in such a way that you set, let's say, the probability of every possible combination of light bulbs instead of individual light bulbs. That's entanglement, right? You can do what you do classically, you just have a switch, but it's a waste, right? And it's very hard to change just one. Classically, it's easier to get to a single record, let's say, in the database or an account in an accounting system. In quantumly, you need a lot of entanglement. Pretty much all qubits entangle with each other to go to that, which is very expensive, right? So going back to the row of light bulbs, you program every possible combination of light bulbs with a probability. Then when you power this row, you get one combination on, the rest off. You power again, one combination and another combination probably, right? It's non-deterministic. But the outcomes will be following whatever you program. There's a probability distribution. So it's similar in some ways, but at the same time, very counterintuitive.
So let me just make sure that I get that. So you set the whole thing up so that there are certain probabilities for certain combinations for you, and then you measure that repetitively a certain number of times to confirm that this is following the distribution that you expected? Is that what you just said?
Yes. And the interpretation of each qubit can be different depending on the problem. For example, it can be, let's say, instruments in a portfolio. So do I buy that? Do I include that in my portfolio or I don't? So this is a binary interpretation for each qubit. But you can also interpret them as digits in an integer, right? And you can use two registers of qubits where the first one tells you what stocks to buy using a binary approach for each. And the second gives you the value of the portfolio. And now you look at the binary digits and you can work with integers for simplicity, right? Real numbers are a little more difficult, but you can do that, right? So different interpretations for what the qubits do, right? But what's essential is to understand that you program these probabilities of combinations of qubits when you write a quantum program.
Yeah, so the interpretation bit, that makes complete sense to me. That's basically how classic computer science works.
Yeah.
The programming bit is a little bit still fuzzy. How do you do that?
So there is only one operation in, let's say, qubit systems. I won't talk about infinite dimensional quantum mechanics and so on. And some of the reviewers of the book, they go there. They say, oh, this is not true for infinite dimensions. But we work with qubits, right? So the only operation is this. You pick a qubit, let's say a light bulb. And then you take all possible pairs that have that. One of them has that light bulb on, the other one off. And the rest is the same in the combination, on or off, right? So if you have n qubits, you have 2 to the n-1 pairs. And then you preserve the probability of the pair, but you move from one to the other. So from the haves to the have-nots, or the other way around. Each gate does it differently, right? When you do this exchange. And this pairwise programming is very common in nature, like DNA or accounting systems. Transactions are between two accounts, right? Even if you have a portfolio, you sell something, you put it in the cash account, then you buy something, you take from the cash. So it's always two. Maybe you're going to say, this is the final state of my portfolio, but someone has to program in the back end, and it will be exchanges between two pairs of accounts. Same thing here. All the gates do this, but with different formulas, right? So this is but it happens in parallel. So the plus is you change all of them instantly. Quantum parallelism. The minus is this is too powerful, this pattern. When do you need, let's say, to transfer between all accounts, in an accounting system? The challenge is find problems that support this pattern. And Shor is like the perfect storm, right? Because Fourier transform also works with pairs. Every gate looks pretty much like FFT, one stage in fast Fourier transform. Shor's algorithm is a perfect example when this pattern, which is called the butterfly pattern, matches. And a lot of people ignore this. People work with big unitaries and they forget when you go to the real computer, you need to work with this pattern, which we call the butterfly pattern. And it's all over the book.
I can certify it is all over the book. Okay, so once you've got a grasp of the foundation, you mentioned a few other things like Grover optimizer, and I have to admit, I have no idea what an optimizer in this context even means.
So let's take the example of the light bulbs again. You want to increase the probability that the light bulbs will tell you the optimal solution for your problem. It can be as simple as find the maximum of a function or the minimum, right? So you have a function which most of the time it's polynomial. It's even quadratic if you look at the Ising model and so on. A lot of problems can be solved with simple polynomials, right? So if you can find the maximum or minimum of such a polynomial, you can solve problems like portfolio optimization and so on. So what the Grover optimizer does, given a function, and this is what Naren implemented and we released yesterday. So you can play with it. You enter the function and then it will create a quantum state and you'll see the graph of the function basically. And after that, you find the minimum or maximum using Grover. And what's essential here is, again, I don't know how technical we want to get, but so Grover uses an oracle, which is similar to the where clause in a SQL, where you specify what you want from a database, let's say. What records do I want? And Grover gives you a quadratic speed up in the number of calls to this query or oracle. Mm-hmm. But you have to provide that oracle, right? And typically that's a hard problem. In Grover Optimizer, that oracle is simple because we say we just want something negative. Mm-hmm. But that means you match one bit because the two complement pattern is native to quantum computing because of rotations, right? So it's easy to find numbers that are non-negative or negative. We say, give me a non-negative. We find it. Then we shift the function down. Then give me another non-negative. It means I move up. Similar to gradient descent, right? You get closer and closer to your solution. And the search, so it's search-based optimization, right? Using Grover. That's why I think the name came from Stefan Werner, chose that name, and that's what we call it.
Fair enough. All right, thank you for that. I appreciate your explanation there. And then what else are they going to find in the book?
So beyond the foundations that we spoke about, and then we've also spoken about Grover Optimizer, but in the second third of the book, we cover core algorithms. So we talk about Fourier transform, we talk about amplitude estimation, phase estimation, and then as we move into the third part of the book, we talk about some essential patterns or methods that are building blocks for solutions. So for example, we have function encoding. Of course, encoding a function in a quantum state is used in finding the minimum or maximum of a function in Shor's algorithm, various other solutions. Also in the third part of the book, we have Grover Optimizer.
So we use the knapsack as an example. Also, we really like the way Manning works. They recommend having a just-in-time approach, not just in case.
Yeah.
So we didn't include even Shor's algorithm, but Shor's algorithm is very similar to the Grover optimizer. So you find the frequency or period of a signal, but in Shor's algorithm, it's an exponential function. In a Grover's optimizer, we have a polynomial function. But any discrete function is actually a polynomial function. It can be proven. So it's not a restriction, right? You can say any function. In the last chapter, we provide a sort of outlook, and we mention a little bit Shor's algorithm and others, but the book is very focused on following this path. We cover all the fundamentals. The most important algorithms are there because they are using Grover's optimizer. And we stop there, right? So there was a question, should we do anything about AI? Or everyone wants AI, quantum AI.
Yeah.
But we realized, again, because Manning wants to take care of the reader, you don't assume knowledge, you don't jump without explaining everything. It would have been a little bit difficult, probably adding a few chapters to the book. And maybe it's another book.
Exactly. I can also attest to the Mannings. When I was writing my book with them, initially it was very frustrating this. Oh no, they don't know this. And oh no, you can't just give them dump knowledge at the beginning. You have to do it just in time. But I think overall it does make a book better. So hopefully you feel the same way. Whose idea was it to write the book?
I was told from the beginning that this approach is different, is more elementary. And I had to do it because, again, that's what we had. We had developers. We couldn't hire new people initially. It was an experiment. And then because I think I am active on LinkedIn with whenever I had something, for example, Grover's optimizer was first a post on LinkedIn about encoding numbers. Right. And you can think, what? Nobody did this? And yes, nobody did this. I think a lot of the academics know it. But because I posted these things on LinkedIn, an acquisition editor, I think, at Manning, they pinged me. And actually, even before, some people said you should write a book about this. And we had a paper that included a tutorial. Charlie, you are using that. We created a paper about quantum computing patterns. And University of Minnesota, I think they used it in a class, other people. So it was more like, oh, this is a different approach. It's elementary. It should be made available, right? So when Manning pinged me, I asked Charlie if she's on board. I asked my daughter if she helped me for about a year, but without multiple people being in the audience, I think they made the approach better. It just happened. It wasn't deliberate. I didn't say, let's write a book. And it's not what people say. You regret if you don't do it, but you won't do it again because it takes all your spare time.
Oh, yes, it does. That's how it goes. Is the book ready now? I think I've seen most of the chapters arriving already in the early access. How far are you from the release?
Late this year, I believe, will be our release.
All chapters are delivered. They will go into the third and final review, and then it will be production.
I think it says early 2025 estimated. Really looking forward to that. For anybody who wants to go and check out the book, you go to manning.com and you look for quantum software, and you find a book called Building Quantum Software by the two of my guests. One more question before I let you go, and asking for a friend. Should all the software engineers be jumping onto quantum computing now, or is it a bit too early for everybody?
I would say that it's more about interest. So if you are interested to know and follow, you should do it because it's easier than you think as a developer. So it's more elementary. In 200 lines of code, you can see how superposition works, how entanglement works, right? Not their effects, let's say, for computing, not obviously the physical aspects. So from that point of view, yes, if you are looking at getting a job as a quantum developer, that's probably not guaranteed, let's say.
Yeah, I don't think I've seen too many of those on LinkedIn lately. Do you think we're going to see Raspberry Pi style cheap quantum computers abundant in any near future? Or is there any particular physical reason why they're going to have to stay confined in fridges and be very expensive?
Well, the
photonic-
fridges depends on the kind of computer. So the ones that need fridges will always need fridges. Or really fuck my understanding. I don't see there being a Raspberry Pi type of quantum hardware available on the market in the near term.
Maybe
Right.
for educational purposes, where you have a few qubits. And I think there are already some of those. I saw a briefcase, right, that you open, and then there are a few qubits in the middle, and you can experiment with them. But that's for educational purposes. You have to keep in mind, when we go to our business, let's say in investments, or they use tens of thousands of classical servers, like 20, 30,000 right, servers. How many quantum computers do you need to beat those? That's why it has to be understood. And the business, by the way, is happy, let's say, to get another model that sees something that the current models don't see, because you use an ensemble, something like that. The business is willing to entertain using a quantum model. But if you have a small computer like Raspberry Pi, it won't be able to beat 20, 30,000 servers.
Yeah, I think my example of Raspberry Pi is more to say abundant and accessible to everybody and not hidden in a fridge somewhere in the IBM bunker in the middle of nowhere. But is there a first principles reason why we're never going to see those? Or is it just like a practical thing that hasn't been demand for it or something like that? Is that like a physical constraint, basically?
Will be available through already lots of different quantum hardware providers are available through cloud service providers. So Amazon Bracket, I believe they have a bunch of different backends. I don't know which all off the top of my head. So there are quantum computers that are accessible through a cloud service.
But at home, I think there is a company called Brilliance in Australia that promised that. So you can get a small computer with a few qubits, and it has to be photons, right? Or because it works at room temperature.
So we're slowly crawling that direction. And hopefully one day every child will have a quantum computer at home to play with. What a bright future. Thank you very much. It's been a real pleasure. Where do people follow your progress outside of going and buying your book?
The easiest is learnqc.com. We created that domain for the book, basically. We have, for example, there HTML implementations where you play with the simulator in HTML. You don't need to install anything. And from there, you go to links like github.com/learnqc. All the repositories are under learnqc. So easy to remember, learnqc.com.
There you go. So now go check it out, and we're going to take a break. Thank you very much, guys. See you next time.
Thank you.
Thank you.
Bye.